Hello, greetings, good morning. Welcome to our second example from Chapter 5 on property relations. Remember, the best way to master property relations is by working through examples. Okay, and so problem 2 is a little longer. And so in this video, I'll take on part A. And then for part B, we'll look at CP. And then we'll come back to CV after we next move on then to part D and show the relationship between CP and CV. So first video will be part A, and part B we'll look at CP. And then in the next screencast we'll move on to part D, show the relationship between CV and CP, and then use that to answer the CV portion of part B. Okay, so without further ado, in part A, we start off by being asked to show that the variation of Cp with pressure at constant temperature is given by this differential. So show that dCp, dP at constant T is equal to negative T d squared V dt squared at constant P. Alright, this sounds fun, right? Alright, let's see if I can get my cursor moving here. So, in part A, okay, how do we begin? All right, so we want to show that dCp dP at constant T is equal to negative T d squared V dt squared at constant P. Okay, and so how I'm going to begin, okay, is let's start by writing out the definition of Cp. All right, I know that Cp by definition is partial H partial T at constant P. Okay, so how I want to start this problem out is I want to work out an expression for H with independent variables T and P. Okay, so I'm going to work out an expression for H with independent variables T and P. Now, we did this in a posted screencast because it's from the Chapter 5 notes, but let's just go ahead and do it anyways. Okay, practice makes perfect. Okay, so if I want to work out an expression for H with independent variables T and P, all right, my first step is I'm going to write out an expression for the total differential of H, all right, the mathematical expression using independent variables T and P. Okay, so I'll have the dH is partial H partial T at constant P dt plus partial H partial P at constant T dP. Okay, so that's step 1. Then step 2, okay, and I should mention I have my equation sheet open that we can reference. Step 2 is we want to go to our equation sheet, well, or just in general, I want to know, is there a Maxwell relationship I can plug in or a heat capacity relationship? Okay, and just looking at this expression, in the first term I see that I have dH dt at constant P, which is by definition Cp. Okay, so step 2 is we're looking to see if there's a Maxwell relationship or heat capacity relationship that we can plug in. All right, and what we're trying to do is, again, we ultimately want a final expression that only contains the variables PVT, right, those physical quantities I can readily measure, or Cp and Cv. Okay. So in this case, I'm going to plug in Cp. So dH will be Cp dt plus partial H partial P at constant T dP. Okay, so now I have partial H partial P at constant T dP. Okay, so I know I don't have a Maxwell relationship for that, but just for completeness, I'm going to go and I'm going to look at my equation sheet. Okay, and Maxwell relationships are here. Okay, and I find I don't have enthalpy, right? And so I made the comment, I know I don't have a Maxwell relationship for enthalpy, all right? So look at the variables that we have in our Maxwell relationships. I'm looking at PVT and S, right? So our Maxwell relationships are basically relating PVT and S, okay? So I don't have a Maxwell relationship that I can plug in, okay? So I'm stuck. So what do you do when you're stuck? You go back to your fundamental equation, okay, for that thermodynamic state function of interest. All right, so we want to go back to our fundamental equation for H. Okay, so now for completeness, let's say you can't remember what that thermodynamic function is for H. Well, I do remember the combined statement of the first and second law. So du is equal to TDS minus PDV. Okay, so H is our convenience function. Okay, so what we try and do in H is we try and switch the role of the conjugate variables P and V in the second term. Okay, so H is defined as being U plus PV. Okay, so that DH is equal to DU plus DPV. Okay, and so for DPV, I apply the product rule. So this is DU plus PDV plus VDP. Okay, so next, I plug that into my expression for DU. Okay, or I plug in my expression DU. So DU is TDS minus PDV plus PDV plus VDP. Okay, so the PDV terms cancel out. Okay, and I'm left with DH is TDS plus VDP. All right, which achieves that goal of switching the role of my conjugate variables P and V. So if I look up here where I was in step 2, what I needed is an expression for partial H, partial P at constant T. Okay, so I need partial H, partial P at constant T. Okay, so how am I going to get that from here? Okay, well, what we're going to do, okay, and so kind of think about this in 2 steps, right? So this, isn't correct mathematical talk, right? But how we're going to tackle it is I'm going to first divide through by dp. Okay, I'm going to divide my differentials by dp. Okay, and then since I can only differentiate with respect to a single variable at a time, I need to hold a second constant. Okay, in this case, we're going to hold t constant. Okay, why are we going to hold t constant? Because what I'm interested in is an expression for dhdp at constant t. Alright, so now that I'm differentiating with respect to one variable while holding the other constant, so in theory these become curly d's. Alright, and I'm left with this. Alright, so next let's simplify it. Okay, so on the left hand side we have partial h, partial p at constant t is equal to, now we have t, partial s, partial p at constant t plus v, and then partial p is just 1. Right, so this term is just plus v. Okay, cool. So now we can go and plug that in to our expression. So now we have dh is Cp dt plus t partial s partial p at constant t plus v dp. Okay, is this final expression good? All right, so this was step 3. Okay, so is this final expression satisfactory? And the answer is no, because that second term contains s. Okay, so I need to get rid of s. All right, so then we ask ourselves again, do I have a heat capacity relationship or a Maxwell relationship that I can plug in? All right, as we commented when we looked at our Maxwell relationship equations in our equation sheet, the answer is going to be yes. Remember, our Maxwell relationships are going to relate P, V, T, and S. So here I have partial S, partial P at constant T, so I know I'll have a Maxwell relationship for that. Okay, so let me start by writing this down, and then we'll go to our equation sheet. Okay, and we'll plug in, and then we'll plug in the appropriate Maxwell relationship. So dH is Cp dt plus ds dp at constant t. ds dp at constant t is here. Okay, so that's going to be a negative dv dt at constant p. Okay, so this will be a negative t partial v partial t at constant p. Okay, let me check that. ds dp at constant t is negative dv dt at constant p. Got it. Okay, and that's plus v dp. Okay, so now I have an expression for h with independent variables t and p. All right, now how does that help us out? Okay, well, what we're interested in computing, right, or what we're interested in showing, is that we want to show that dCp, dP at constant t, is equal to negative t d squared v dt squared at constant p. All right, so we want to show this. So what we want to compute is, so what we want is partial Cp, partial P at constant T. We want to know how the constant pressure heat capacity Cp changes with respect to P. And again, as an aside, as we talked about in the last screencast, common misconception I have with students is that it's the constant pressure heat capacity, so it should be independent of pressure. Okay, but remember that is not the case. What we have here is, so Cp is going to be, it's a thermodynamic state function, right? So if I have a single component, single phase system, I have 2 degrees of freedom. I need to use 2 intensive thermodynamic properties to pin down the state of my system. So if I use T and P, if I were to plot Cp as a function of P and T, the result is a 3-dimensional surface. So what I'm looking at here is if I cut through that 3-dimensional surface with a plane at constant T, the result will be a 2-dimensional surface of Cp versus P at that fixed T. So here, what we're looking at is how Cp changes with respect to P at that T. Okay, and kind of the other way to think about this is, you could also think about cutting through this. If I have enthalpy as a function of P and T, I cut through that enthalpy surface at a plane of constant P, and then Cp is just a slope dH dt at constant P. Well, if I were to use a bunch of different cutting planes at different P values, we would expect the slope to be different, right? Because if I have, say, a gas phase, I know that gas phase is going to be highly sensitive to pressure. But anyways, so we want to show the dCp, dP at constant T. We want to show what that is, or we want to obtain a relationship for such. Now, looking at my equation of 4, how the heck does this help me? All right. Well, how it's going to help me is I don't know what to do with this, right? I have dCp, dP at constant T, but how I get that, or even get close to that from my expression in 4, right, is beyond me. Okay, so what we're going to do is we're going to apply a trick. Okay, the trick is remember, by definition, Cp is partial H partial T at constant P, right? It's enthalpy with independent variables T and P, the same independent variables I'm using here. Okay, so this would be equivalent. So partial Cp partial P at constant T would be equivalent to, okay, I'm going to plug in for Cp, partial H, partial T at constant P, then the differential of that with respect to P, holding T constant. Okay, good. So that's cool. Okay, but again, if I look at my equation from equation at step 4 there, it still doesn't really help me out at all, because dH dt at constant P is just Cp, and then I'm stuck, exactly where I was in the beginning. And so what I'm going to do is, I remember a property of mixed derivatives is that the order of differentiation doesn't matter. So I could equivalently write this as partial H partial P at constant T, and then differentiate with respect to T, holding P constant. Okay, so then the question is, does that get me any further? Okay, well, if I look up here at 4, okay, dH dP at constant T is just this term, all right? And if you want to show that to yourself, well, you could do it in one of 2 ways. Well, one would just be taking the equation in step 4 and matching with the equation in step 1, right? dH dP at constant T is just the second term in brackets. Okay. The other way would be just as what we did in step 3 here. Okay. What you would do is you would divide your differentials through by dP, holding T constant, at which point you would have dH dP at constant T the first term would go away because you'd have dt dp at constant t, which is 0, t is being held constant, and then you would just have then that second term in brackets is equal to dh dp at constant t. Okay, so we have dh dp at constant t is equal to negative t dv dt at constant p, negative t dv dt at constant p plus v. Alright, so that gives me dh dp at constant t, and so what I now want to do is I want to apply the differential operator to this expression, because what I want is the differential with respect to t at constant p of this equation. Alright, so partial, so if I plug that in here, okay, so I'm writing this out in all of its glory so that hopefully it makes sense. Okay, so now I could plug in for dh dp at constant t this expression. So what I'm trying to differentiate then is negative t dv dt, and actually I'm going to write it out in a slightly different form just so I can write this a little bigger. So I'm trying to differentiate with respect to t, negative t dv dt at constant p plus v. Okay, and all of this is being done at constant p. Alright, so now what I need to do is differentiate said expression. Alright, so now I'm applying the differential operator to the expression in parentheses. And so let's do it. Alright, so remember p is being held constant. So what I'll first do is, looking at this first term, right, is we're going to have product rule. Okay, so I'm going to have negative, well, and I'm going to factor, well, pesky negative sign. Okay, so if we deal with this is a negative of t dv dt at constant p, so I'm going to have negative. I'm going to factor out the negative sign, and then I'll have t, and then dt, d dt, dv dt at constant p, right? So dv dt, this is already differentiated with respect to t at constant p, and now I'm going to apply the differential operator at constant t holding p constant. That gives me a second derivative, d squared v dt squared at constant p, okay, plus dv dt at constant p times, now I apply the differential operator to this term, that's dt dt at constant p. Okay, I'll put that in brackets because all I did is bring out the negative sign, and I'll apply the differential operator to this last term. This is plus dv dt at constant p. Okay, alright, so let's see what this gives us. So if I put that negative sign back in here, I have negative t d squared v dt squared at constant p plus dt dt at constant p is just going to be 1. So this will be, not plus, because now I'm distributing the negative sign. So this will be minus dv dt at constant p plus dv dt at constant p. So these two terms cancel, and we're left with partial Cp, partial p at constant t is equal to negative t d squared v dt squared at constant p. Cool. So we just showed, starting from the combined statement of the first and second law of thermodynamics, that dCp dP at constant t is equal to negative t d squared v dt squared at constant p. So now it's been so long since I saw what the answer was that we were given to start with. We're going to go back up and peek. Okay, and we were asked to show that dCp dP at constant t is negative t d squared v dt squared at constant p. Yeah, so we got it. All right, and so that was cool. Starting from essentially, the combined statement of the first and second law of thermodynamics and a little bit of calculus, we were able to prove that relationship. Right, which tells us how Cp changes with respect to pressure at a given temperature. Nice. All right, now I said we're going to look at the first part of B. So in B, it says use this result to show that Cp and Cv in the ideal gas state are independent of pressure. Okay, so I'm going to show this for Cp, and then we'll come back to Cv in the next screencast when we look at D. And in D, we're going to show the relationship between Cp and Cv. So that it becomes trivial to show. All right. Just show that this means for an ideal gas that heat capacity is independent of pressure. Okay. Okay. So in B, we want to show that for an ideal gas, partial Cp partial P at constant T is equal to 0. All right, which would tell us that Cp is independent of pressure. All right, and so how we're going to do this is, okay, if we had just first been if we started with asking this question, we'd be sitting there and saying, what do we do? Okay, but now that we've worked out this expression for dCp dP at constant T, where this is really a mixed derivative of enthalpy with respect to temperature and pressure. So this is equivalent to negative t d squared v dt squared at constant p. So in order to evaluate this derivative, I need an expression that relates p, v, and t. Okay, so to evaluate this expression, I need a relationship that relates p, v, and t. Well, for an ideal gas, okay, and I'm going to emphasize this is for an ideal gas. For an ideal gas, we have the ideal gas equation of state that PV is equal to RT. Okay, so V is equal to RT over P. All right, so I need d squared V dt squared at constant P. I need a second derivative, so I'm going to start with the first derivative. Okay, so just to make it absolutely clear, okay, d squared V dt squared at constant P is equivalent to dV dt at constant P, and then differentiate this again with respect to T at constant P. Right, it's a second derivative. And so what I'm going to do first is let's calculate dV dt at constant P. Okay, well, that's going to be the differential of RT over P with respect to T at constant P. Okay, so P is being held constant. R is my molar gas constant, which is constant. So this is R over P, partial T at constant P. Okay, where dt, all right, that's just 1. Okay, and so we're left with dV dt at constant P is equal to R over P. Okay. So in the next step, all right, I want to differentiate that result with respect to T at constant P. So that's going to be the differential of R over P with respect to T, holding P constant. Okay, well, P's constant, R's constant, so this is just the derivative of a constant with respect to T. Derivative of a constant is 0. Okay, so you just proved for an ideal gas that dCp, ideal gas, dP at constant T is equal to 0. Therefore, an ideal gas for, Cp is independent of pressure. So Cp is only a function of temperature for an ideal gas. Okay, Cool. You just showed that the heat capacity of an ideal gas is independent of pressure. You just proved that from a combined statement of the first and second law. All right. Now take that in. All right. Think about everything we just did. I know it was a long process to get to this, but you just proved that the heat capacity of an ideal gas is only a function of temperature. The heat capacity of an ideal gas is independent of pressure. And all that required was the combined statement of the first and second law of thermodynamics. Yes, we went and we plugged in a Maxwell relationship, but those all originated from our combined statement of the first and second law if you were to go back and look at that screencast. All right, and so, there is, a quote. So I remember from Ken Dill's book on molecular driving forces that thermodynamics is two laws and a little calculus, right? And it kind of is true. All right, so, all right, cool, man. Hopefully that, makes you feel cool and gets the thermodynamic juices pumping, huh? All right, we'll look at the rest of this problem in the next screencast.